Anyone? Any solutions? Any answers? Okay. Problem one is just to write the dual. And so we know we've got like almost a cooking recipe for making dual problems. So when the primal says maximize, the dual will say minimize. Now, there are two of these functional constraints. So there's functional and then there's non-negativity constraints. There are two of the functional constraints, which means I will need two dual variables, decision variables. Usually we call them y1, y2. And the right-hand sides, we know they become the dual objective coefficients. And then the constraints go the transposed way. So we'll have, so the first constraint will be 3y1 plus y2, because there's a 3 here and a 1 there. And that should be greater than or equal to 5. And then we have 2y1 plus 3y2 should be greater than or equal to 20. And now, because the sign in both constraints is less than or equal to, we want y1 and y2 to be both non-negative. So y1, y2 is greater than or equal to 0. End of answer to question 1. Right? Anything still unclear about this? At least to the people who have been coming here. Okay. Now, the second question was to solve it using the first stage procedure. Okay, so since people are writing them down, I'll just write it. So the first stage procedure, you know that the first tableau will have, well, y1 and y2 are the decision variables. Then we had s1, s2, and two artificial variables because each of the first two constraints, well, each of the two constraints is a greater than or equal to constraint. So in the basis we'll have a1 and a2, and then we have the artificial variable, the original variable z, and we have the artificial variable g. This is the shape of the tableau. Okay. Now the right-hand sides are 5 and 20. The z gets a 0. The coefficients I'm just copying, 3, 1, 2, 3. These are surplus variables, not slack variables, so we have to have -1s there. And the artificial ones are in the basis, so they have to look like this. And then also in the basis, so they have to look like this. The objective is 160, 200. The Z objective, and the artificial objective is 210. Yes. Right, thank you. So minus 210 there. It's starting to be unreadable, isn't it? Yeah, so if you don't remember, you should have revisited it, but in the G row, we get the sum of the rows with artificial variables, except zeros and in the A1 and A2 columns. So when I add them together, I get 25, 5, 4, minus 1, minus 1. And then there is some pivoting, which I don't want to do all of it. I'll just give you the final tableau. After we've, all right, so this actually is no longer there. It turns out that the optimal basis is Y2S1, Z. The values, sorry, 20/3, 5/3, and 1400. And this was Y1, Y2, S1, S2. Two-thirds minus 7/3, 20. Y2 is in the basis, so not much surprise there. S1 is also in the basis, so this is what it looks like. And S2 should be minus 1/3, minus 1/3, 70. Okay, now I've forgot to bring my solution to the first homework problem. Has anybody got that by any chance? Because you were supposed to, what did it say? Compare the solution to the primal solution. No one? Anybody volunteer their solution? Because I forgot to bring mine. Well, okay, so if you haven't, then check it at home with the first solution. So you'll be seeing the same numbers, except, well, these ones will be in the original objective row, and these ones will be in the original val column. The 1400 should be the same, and these numbers in this area should also be the same as in that tableau, but just transposed and slightly arranged. But it shouldn't be any surprise there. Okay, any questions about this? And this one looks like this. So this is the same thing we did before. Maximize. Okay, so the dual has minimize. Three constraints. So there are three y's: y1, y2, y3. 4, 12, and 1 go in the objective. 1 and 1 go into the right-hand side. First constraint is 1, 4, minus 1. 1, 4, minus 1. Second constraint, 2, 2, 1. 2, 2, 1. The only thing that's new is when you have an equality constraint, okay, rather than a less than or equal, you don't ask for y1 and y2 to be non-negative. We need y3 to be non-negative because if it's less than or equal to it, but y1 and y2 can be negative if they want to. Why is that? Well, if you recall what we were doing, we were multiplying each of the constraints with the respective y variables. So y1 times this one, y2 times this one, y3 times this one. We wanted y3 to be greater than or equal to 0 so that the sign wouldn't flip the wrong way. Okay. But if the sign is equal, then it doesn't matter that it's negative. It won't flip because it doesn't be. So in this case, the answer is this. Good. Everything clear? The people are still copying. Things they should have done as homework. Oh. Okay, let's move on then. Right, so last week we did this week duality theorem. We said that you look at the objective here and the objective of the dual, they're always in this relation. And I promised you that in the optimal solution they will actually be equal. So that's what the strong duality theorem says. But it says even more than that. It deals with the cases where some of the problems are infeasible as well. So just as a reminder, so what does it mean that a linear program is infeasible? It's infeasible if yes, it has no solution. Yeah, it has no feasible solution, I would say, but that's probably what you mean. So if it has no feasible solution, which means that there is no x that would satisfy all these constraints, or in this case, there is no y that would satisfy all these constraints. Okay? That's infeasible. And then, do you remember what was the second possibility for a linear program to have no optimal solution? I think it was one of the exam questions as well, maybe. Anybody recall the second possibility for a linear program to have no optimal solution? Yes? Infinite solution. Infinite, yes. It was called unbounded on that. It's kind of infinite, but it's not really. So it's called unbounded if the objective function can be made as large as we want, so arbitrarily large for maximization or small, and that's for minimization. Okay, so we had examples of this last year, so I won't spend much more time on it. But look at this. If P is not infeasible, so if P has a feasible solution, then D be unbounded. No, why not? Because it says down there, isn't it? No, it cannot, because if I find a feasible solution, I can find some number, a finite number here. And that gives me a lower bound. So when I'm trying to make this as small as possible, I can't, because there is a number that I can't go below. Okay? So if I find a feasible solution to this, and this value that I get here won't let me make the dual objective as small as I want. There will be some value. Symmetrically, if I find a feasible solution to D, then I'm going to get an upper bound here, some number, and I can't increase my profit or whatever objective of the primal beyond this number. So because of the weak duality theorem, if P is bounded, if P is feasible, D can't be unbounded. And if D is feasible, P can't be unbounded. So those kind of easy observations. And actually that is already the first bit of this theorem, or the first two. Part of the theorem, really. It's just a contrapositive, as it's called, but really is the same thing. So when we want to, I've not read the theorem, I'll be reading it bit by bit, but the bits 1 and 2 we've just talked about. So to prove number 1, if D is feasible, then P is bounded by the weak duality theorem. Okay? And that's a contrapositive of what is being claimed here. Now, 2 is, well, it's the same thing, so I'm just writing it to waste some time. So if P is feasible, then D is bounded, because for the same reason. So now I'm going to draw something. Drawing a table. So what can the dual be? Infeasible, or unbounded, or feasible and bounded. Okay, and the primal can also be infeasible, or unbounded, or feasible and bounded. there are these three options. Now, some of them cannot happen, can they? So we just see that if P is unbounded, then D must be infeasible. So these two cannot happen. And if D is unbounded, that's part 2, then P is infeasible. So this cannot happen. So what is the third point saying? The third point is saying that D is feasible and bounded, then this cannot happen. We must be here. But also, if D, and second thing it's saying, if D is feasible and bounded, then this cannot happen, and we must be here. Okay. So that's kind of the ideal case. This is when we have optimal solutions. Both exist. And so this, we don't know. We need to prove that point 3 is saying that this cannot happen. And this cannot happen. How about the remaining 3 boxes? Can they happen? What do you think? Yes. So it's possible that both are infeasible, and it's possible that one of them is infeasible and the other unbounded. All these things are possible. But in none of these cases there are any optimal solutions. So if P is infeasible, it doesn't have an optimal solution. If P is unbounded, it doesn't have an optimal solution, and the same thing for the dual. And so these 3 this week's homework exercises give you examples. Well, they give you an example of one, and they tell you to invent an example of another. But now let's concentrate on something. Now, if we want to prove this part 3, we should say that this is not possible. And then the second thing that it says is that when we get optimal solutions, then they actually have the same objective value. So these are the 2 things we want to prove for part 3. So for part 3, we trust the simplex method. And so we trust that if P is feasible and bounded, the simplex method finds an optimal solution. So what's the optimal simplex tableau going to look like? It looks a bit like this, doesn't it? So we have Z, we have some bases. What do we have here? Well, part of the exercise that we were doing, well, part of the lectures that we were really doing, was to find out that this was a matrix that we called MB inverse. Okay, that's some sort of matrix. No, then we knew that this was, we call this like this, or maybe with a dash, but that doesn't really matter. Okay, so these were some combination of these rows here. And in this row, the vector that sits there is this one. Oh, I forgot one column, didn't I? There's also the val. And in the val, we knew that there was MB inverse B. And all these letters, so, yeah. Forgotten what MB inverse is, doesn't really matter. Now, it matters, but it doesn't matter. And B and C and A, they come from the original formulation of the primal. So if you have the slide in front of you, they say what A, B, and C are. So this was the optimal solution. Now, how do we know that this tableau is optimal when we see it? When we see a tableau, what defines optimality? Which row do we look in? Yeah, the Z row. Exactly. So we know that there's no more negative numbers here, because that's what we're maximizing, so we don't want any negative numbers. So optimality means that this vector is greater than or equal to 0, and this vector is greater than or equal to 0. That didn't fit. And feasibility, how do we know that we even have a feasible solution? Where do we look? Okay. There are negative numbers in the val, then there's something wrong, right? It's not feasible. So feasibility means that this is non-negative, so MB inverse B is non-negative, and that's everything we need to know. Okay, so this is the feasible, so this is the optimal, sorry, tableau. If we're now, what I will try to prove is that the optimal solution of the dual problem is what we find here in this portion. So let's take y star, which is going to be this, except we don't want a row vector, so we want the row vector transposed, which is going to give us a column vector, because we want the column vector to be the optimal solutions to the dual. Okay, so this is non-negative because we have this. Okay. So from optimality, we get that it's non-negative. Now, what else do we want to, well, we want to show that this y star is an optimal solution of the dual. So we should show that it's feasible, and also that you cannot have any better value. So what does it mean? So feasibility, when you look at this dual again, wrong way. So we want to show that, well, for feasibility, we want to show that it's greater than or equal to 0. We've already done that. So we also want that other inequality coming from the matrix. So what's that mean? So AT y star is well, okay. So this is just a number. No, it's not just a number. AT y star, no. Okay, I'll do it this way. So if I do a transposition on this, okay, that's going to give us an easier. So this is y star transposed times A. Now y star transposed is that over here because we know that what y star is. So this is CB slash B inverse A. And this is greater than or equal to C because we have that. So therefore, AT y star transposed is, so when we transpose what we got, we get what we wanted. So that's the second thing now. That's the end. So this y star is a feasible solution of the dual. Is it optimal? I don't know. So what is the objective? Well, it's this. Which is that, because we defined, doesn't show anymore, but that's the definition of what's that. We just put it in. Oh, yeah. That's just transposing everything, which we can do because that's just a number. It's not a vector, the objective. So again, same trick as last week. We can transpose it. We get this. And so this is, I'll just call it CB times CB dash probably here. XB. Oh, yeah. So there's a like a kind of a trick. What's this? Well, it's kind of like the vector of is the optimal solution to P. Next star we get from the tableau where there was MB inverse B. Except we have to pad it with zeros for suspenders. Not doing much. It's only reshuffling the variables in the right order for the basis. But the values in X star with the list B and in X star without the list B are the matrices. And so what am I doing? I think I need this here. And so, yeah, that's what I need. That's exactly what I'm saying, I'm just not writing it in the right way. I understand people can be confused, but it's there's not much to be confused about. So now we have a feasible solution of P and a feasible solution of the dual. And when we look at the two objectives, what do we see? Well, we see that the objective of the dual with this Y star has the same value as the objective of the X star, so of the primal. And the weak duality theorem tells us that when we're trying to minimize the dual, the least we can ever get is that value. That's what what's there for. I mean, it was there for the dual thing, but one of the things that there is there for. So if like I have this lower bound on what the objective of the dual can ever be, and if I reach it, that means I've found an optimal solution because I can't get any better one by the weak duality theorem. And so this is optimum. And that's the end of the proof. And that's enough proofs for a reasonable amount of time now. That's maybe a bit hard to pass the first time you read it or see it, but you just have to come back to it and read it again. And it's going to get better eventually. Okay. One last thing about this is kind of the interpretation of duality. So now, because of the strong duality theorem, or if we're assuming that we have an optimal solution, what do we get? So we have this optimal objective, which is equal to C times some optimal solution of the primal, but it's also equal to BT times the optimal solution of the dual. And this we can just rewrite as, well, the individual right-hand sides BI times by the individual variables, and we're summing them over all the i's. Okay, so that's the inner product of two vectors. So y star is the optimal dual solution. Now, if we have, like we used to have, the examples where the x's were some, so xj is level of some activity. For example, the first example was how many chess sets to produce. Okay, and then the CJ was the unit profit of this activity. So we had how much profit every small chess set makes, and how much profit every large chess set makes. And then what was BI? BI was the amount of some resource available, wasn't it? Now, what is this telling us? This is telling us that I can increase the amount of resource available. What's going to happen to my optimal profit? It's going to increase by the value of the dual optimal solution. So in some sense, this dual optimal solution is the amount of profit which is contributed by 1 unit of that particular resource. Do you remember the chess problem? It's like this. the three resources we had in this example were the lathes, the wood. We only had 200 kilos of wood every week. We had 31 hours of finishes time per week. And when we found the optimal tableau, it looked like this. Not. So now we know that these numbers give us the optimal solution to the dual problem, which is proved it in the strong duality theorem as a byproduct. So what does this mean? This means this is zero, so the lathes are not contributing anything. If we add more lathes, the profit is not going to change at all. But if we could add an additional kilogram of wood, we would be earning, what, £1.67 something more a week. And if we could add an additional hour of finishes time, we would be earning this much more every week. And that's kind of the interpretation of what the dual solution does for us. This was, I think this was quite dense today, but I think from next week it's going to get a bit more examples and a bit more applications. So that's it for this week.